Well, hey there, you guys. Mrs. Grady here, looking to give you a little bit of help when it comes to practice number one. I expected these to be a little bit bigger when I cut and pasted them, but luckily I'm pretty sure you've got your workbook right in front of you, so this should not be a problem. All right, let's go through some of these and make sure you're on the right track and you have the correct answer. So question number one about an astronaut throwing an empty oxygen tank. That is a classic explosion problem. Oops, let me stand in a different spot so I can write and it sort of makes sense. All right, that is what we call an explosion. Hopefully you can read that. That's not the way it's really supposed to look. What that means is that you have something that is together and then it is no longer together. So our initial momentum has got to be zero, but that also means that our final momentum has got to be zero. And when that is the case, what ends up happening is you end up with something moving in the negative direction, and that's kind of handy. So let's consider together the before of the explosion. Here's our astronaut. All right, I am uncalibrated here, folks, so I am going to pause this for just a moment, and I'm going to recalibrate the board, and I will be right back, so that way this makes a little bit better sense. Okay, let's give that another try, shall we? All right, so like I said, this is what we call in physics, we call it an explosion. And we've got our, let's see if I can write it in it. Looks like, oh, there we go. Well, that looks almost like where I'm putting the pen. All right, so let's say here's our astronaut, right? And at first he's holding on to the tank. Your initial momentum is going to be zero for those two objects. It says he's at rest. Perhaps he's floating in space, but you don't have any information on that. And then what happens is Mr. Astronaut guy, he starts to go this way. I don't know where his arm went, but the tank starts to go this way. So again, one will be positive and one will be negative. That will cancel out and still add up to a final momentum of zero, which is pretty nice. So that's the key thing. You want to take that snapshot before he throws the tank away and after he throws the tank away. The setup mathematically looks a little bit like this. Now I know some of you like to use charts when you do this, but I like to do it as a giant algebra equation. It ends up working out to be the same thing. So zero is our initial momentum. The final momentum is going to be the mass of the astronaut times the velocity of the astronaut plus the mass of the tank times the velocity of the tank. And this is how, if you're doing it algebraically, I definitely want to see it like this. I want that zero on the left because then I'm going to be able to tell that you know that this is an explosion. All right, that's supposed to be 80 times V. That didn't really, wasn't really legible. I apologize. All right, plus, now the tank is 10 kilograms, and I'm being lazy here. I'm not putting in the units, but I think you get the idea. Okay, so this equals 0. So you can see that I'm going to get a negative velocity for the astronaut, and that's just fine. If you don't want to get a negative velocity for the astronaut, then make the tank negative instead. I don't care. As long as I can see the setup and that, you know, what it's like looking like there, making sure they have two different directions. That's really rather critical. All right, let's move on to our next question here. All right, this is the melon. Melon's on, yeah, I think this cracks me up. I didn't want to put the picture on there, but all right, again, let's consider what's going on here. The original snapshot, there's this guy, and he has a melon on his head, and there's an arrow headed for the melon. All right, so initially, this has all the momentum. And then in the end, the final snapshot is, you know, let's face it, there goes the melon. It'll have some velocity, and the arrow has velocity as well. So you could, I mean, if you want to do the bar graphs like we were doing before, you could consider that, sorry, I was looking at the wrong question for a minute and I got myself a little bit confused, that the arrow has momentum to start with. The melon doesn't have anything. And then if you take the second snapshot, the arrow has some momentum, so does the melon. So it's kind of splitting up that velocity. You expect the arrow to slow down, and it does. All right, so let's consider it in terms of a conservation equation. The initial momentum of the arrow equals the final arrow momentum plus the momentum of the melon going off the guy's head. So when I set this up, all right, the arrow has a mass of 0.25 kilograms. It's moving at 30 meters per second. The arrow still has the same mass. It hasn't shattered into a million pieces, so that's supposed to be a 5. Sorry if that's a little tough to read. All right, so 0.05 kilograms, but after the collision, after it goes through the melon, is moving at 18 meters per second. And the melon is 2 kilograms, and we want to know how fast it is moving at the end. So 1.5. Okay, I don't know what happened there. Let's try that again. I hit the thing with the book, and all of a sudden, bam, I have a giant line on there. All right, so I do a little algebra, 0.9 plus 2v. I'm going to move the 0.9 over. I'm going to get 0.6 equals 2v, so I get v of 0.30 meters per second. Also positive, so it is moving in the same direction. There we go. Hopefully that is a fairly easy setup for you. Let's move on to number 3. Oh, this one I like because it works with 3 objects, and that's not something we usually are thinking about. But let's consider what's going on here. You've got this raft, and then you've got the swimmers on the raft. Okay, I'm still a little bit off here. I have a disembodied swimmer. This one goes this way. This one goes this way. We want to know what the heck's going to happen to the raft. All right, the raft is going to eventually move. So what you consider is that everything is together to start with, right? You have the initial momentum is going to be of swimmer 1, swimmer 2, and the raft, because they're all together. And it says that it's motionless. So that means it's 0. This is another classic explosion question. When we're done, we have the momentum of swimmer 1, the momentum of swimmer 2, and the momentum of the raft, which is the one we want to know about. It also says that the swimmers go off in opposite directions. This is another one where folks sometimes will, first find swimmer 1, then find swimmer 2. They figure out, okay, those are in opposite directions. What's the difference? It's got to be made up by the raft. And if that's how you figured it out, great. Again, I like to do things in a nice line. I like to do things in a nice algebraic line. So the swimmer number 1, mass of 50 kilograms. And I made this one the positive 3 for his velocity. You can make it negative. It doesn't really matter. All right, it's just going to change. It'll just change the sign on your answer. Your second swimmer has a mass of 80. I figured he's dropping off the opposite end of the raft, so I made him negative 3. Again, if you flip this one to positive 3 and then the 50 kilogram swimmer to negative 3, you'll still end up with the right direction for the raft, which is good. So 180 is the mass of the raft, kilograms, times v. When I then set this up, I'm going to get 150 over here. I'm going to get minus 240 over here, and I'm going to get 180 times v. It's pretty easy algebra by now. So 0 equals negative 90 plus 180v. 90 on the other side divided by 180 equals v. So I get a velocity of about ½ meter per second. And since it's positive, that means that the raft is going in the direction of the 50 kilogram swimmer. Hopefully that makes sense, right? Because the other guy has more momentum, so the raft compensates by going the direction of the lighter swimmer. I'm going to change color here because it's getting a little boring doing black the whole way here. All right. Whew, it's warm in this classroom. Okay. We're going to do measure velocity, muzzle velocity of a bullet. Okay, this is a classic experiment as well. So if you've got this bullet and it's fired, it's going to get embedded into a piece of wood that rolls on this cart, and off it goes. Highly artistic rendering here. I know you're impressed. All right, so the bullet has momentum to start with, and this whole contraption together with the embedded wood, or the embedded bullet within the wood, has a final momentum. So when you set this one up, you figure that the momentum of the bullet equals the momentum of the wood, the cart, and the bullet put together. and you're curious to figure out the velocity. The key thing here is that the velocity, oh, you want the initial velocity of the bullet. The key thing here, though, that you have to keep in mind is when you're dealing with this one over here on the right-hand side, that is the same velocity for all three objects. And, oh my goodness, look at this. They didn't tell us outright how fast it's going after the collision. But you know what? They told us that it is moving, and it's moving 80, it's moving with a constant velocity. So it's moving 0.80 meters in 0.4 seconds. Okay, well, you can figure this out. You've done it a million billion times, right? 0.80 equals v times 0.4 seconds. So your velocity actually works out to be 2 meters per second. That's the post-collision, right? So grams to kilograms for sure. Don't forget that. It's a very tiny bullet. We're looking for its velocity. We would expect it to be a pretty big answer here. And then you're going to add together the 10 kilograms and the mass of the bullet because they're combined and they're moving with a velocity of 2 meters per second. So when you do the math and you figure this one out, you get 402 meters per second. It's critical that you make sure that the masses are in the same unit here. Otherwise, your answer is going to be off by quite a bit. All right, but do realize that this is what we like to call an inelastic collision, where you have two things that stick together. Then there's going to be more coming on that in a little bit. Last but not least, we have another explosion. It's with the cannon on wheeled carts. So again, you've got this cannon. You know me, I can never draw anything. And the cannon's going to go one way, and the cannonball is going to go the other way. So important for us to figure that this is, again, an explosion where my initial momentum is 0. When it's together, this is the post-collision, really, this whole shebang, right? But while the cannonball actually has while the cannon actually has the cannonball in it, and it's just sitting there, you have an initial momentum of 0. So 0 equals, you want the momentum of the cannon plus the momentum of the ball. So 0 equals. All right, let's see what we got here. We've got 150 kilograms for the cannon itself. It has a 1.5 meters per second recoil. And the cannonball, I think, is 10 kilograms, and we want to know the velocity. All right, the velocity is going to be negative the way I set this up. If you made the 1.5 meters per second negative, then you'll get opposite signs on this. It doesn't honestly matter, but that's a 22. Sorry, oh God, that's even worse. All right, 22.5 meters per second. Whiteboard writing is not always the prettiest writing, but at least you get a little bit of a full explanation. So hopefully that is helpful to y'all, and I will talk to you later. Next is going to be elastic and inelastic collisions.